Very good morning to all of you. My name is T. Rajita, lecturer in ECE, Government Polytechnic, Mamnar. In this semester, I am dealing third semester. Subject is network analysis. And I am going to discuss the topic maximum power transfer theorem. In the last class, we discussed different types of theorems, that is Thevenin's theorem, Norton's theorem, and superposition theorem, like that. So by using all these theorems, we can analyze the circuits. So on completion of this period, you would be able to state maximum power transfer theorem and understand the maximum power transfer theorem. And you can solve some problems also on this. What is maximum power transfer theorem? So this is very important theorem in the circuits because everywhere the power has to be transferred from one place to the other place. In any communications, we have to transfer the power from one place to the other place. So in that time, whatever we want to power transfer must be maximum. So for that maximum power, we are stating some theorem. So when it is possible for maximum power transfer, when it will be minimum power transfer, that is very, very important to issue. So that is the reason we are going to study this maximum power transfer theorem in this subject. So in this, the statement is the maximum power can be transferred to the load from a source when a load impedance is a complex conjugate of the source impedance. Generally, in practically, all the loads are impedances, not resistances. Whatever in ideal conditions we are going to study, the load is a resistor. But in practically, all the loads will be the impedances, because at higher frequency, all communications are used at higher frequencies. All of you know that different communications, that is radio communications, telecommunications, mobile communications, or radar communications, or satellite communication. All the communications are using radio frequencies or more than microwave frequencies. So at these frequencies, the load must be an impedance. It's not a resistance. If we are using a resistance also, it is having some reactive component. So load is something, whatever the Z, there will be a circuit impedance is R plus Jx, then the load impedance is R minus Jx, then only there will be a maximum power transfer theorem. Transfer will be done. So transfer of the power should be maximum when the circuit impedance must be equal to the complex conjugate of the load impedance, or load impedance must be is equal to the complex conjugate of the circuit impedance. This is the theorem. So source impedance is R plus Jx and load impedance is R minus Jx, where R is the resistance, X is the reactance. If X is a inductive reactance, then in load it should be the capacitive reactance. A circuit impedance, the reactive component is inductive. Then in load, the reactive component must be a capacitive, and in both the cases, the real part must be is equal to the same. So Z is equal to, that is R plus Jx, then the load impedance must be R minus Jx, then only the maximum power will be transferred to the load. That is the theorem. So maximum power transfer theorem for DC networks. First we will study about the DC networks, then we will go for the AC networks. See here, the maximum power is delivered from source to the load when the load resistance is equal to the source resistance. Here there is no question of the reactance because it is DC and there is no reactive component will be there. So it's a simple. This is the circuit. Suppose a voltage source is there Vs with internal resistance or Rs and it is connected to load RL. When this power is maximum transferred to the load when the Rs must be equal to RL. That is the statement. Now we want to go and prove the theorem. Take this circuit. In this circuit, Rs is the circuit impedance, RL is the load impedance. Now the current in the circuit I is equal to Vs by Rs plus RL. So power delivered to the load RL is equal to I square into RL. See, P is equal to I square into RL, where by replacing I is equal to Vs by Rs plus RL. So P is equal to Vs square RL by Rs plus RL. This is the power. So we know the equation of the power. Now what is our aim? To find out the maximum power. So the maximum power, how to find out that maximum power? Means the power is varying with the load. If a load is going on varying, the power delivered to the load is also be varied. So when is the maximum is or minimum? How to find out that? We know the equation. So in a mathematics already you studied about maximas and minimas. So when the maximas or minimas are occur, when the differentiation of the equation or a function, and the differentiation of that function is equal to 0, then that may be a maxima or a minima. So if how to find out that maxima or minima? So if the function is double differentiated, if it is negative, that is maxima. If it is positive, that is minima. So in that already we studied in the mathematics. Now we want to find out the maximum power transfer of the load. So maximum power transfer to the load, how to find out? We have to differentiate the power with respect to RL. That is the important. See, now I am going to explain about that. To determine the value of RL for maximum power transfer, to find out, first to differentiate that dP by dRL is equal to 0. First differentiate with RL and equate with the 0, because we are assuming that there is a maximum power is transferring. So for maxima or minima, the differentiation of power with respect to load is equal to 0. So that is the reason we are going to differentiate the power with respect to RL and we are going to equate it with the 0. So by differentiating this, d by dRL, V square RL by Rs plus RL is equal to 0. So then by differentiating this, see here, in numerator it is RL is there, in denominator is also RL is there. So numerator and denominator in both cases it is RL is there. And you have to differentiate by U by V method. So by doing this differentiation, what we are getting, Rs plus RL whole square, Rs plus RL whole square minus RL into Rs plus RL by Rs plus RL whole square. See here, V square is the constant. We are taking it out into that and differentiate with respect to RL. See, U by V method, RL Rs plus RL whole square minus RL into 2 Rs plus RL by Rs plus RL whole square. So that is equal to 0. So by solving this, what we are getting here, see here, Rs plus RL whole square minus 2RL into Rs plus RL is equal to 0. We are equating it with 0, so the denominator is going to 0 and numerator becomes, it is Rs plus RL minus 2RL plus into Rs plus RL is equal to 0. So from this, Rs square is equal to RL square plus 2RsRL minus 2RL square minus 2RsRL is equal to 0. 2RsRL is cancelled and RL square minus 2RL square is equal to RL square. So that is equal to Rs square is minus RL square is equal to 0. So Rs is equal to RL. So in a DC circuit, the circuit resistance is equal to the load resistance. In this way, we can prove that there is a maximum power can be transferred only when the load resistance is equal to the circuit resistance. When the load resistance is less than that Rs, the maximum power is not transferred. When the load resistance is greater than the Rs also, the maximum power is not transferred. So when both are equal only, then the maximum power will be transferred to the load. That is the condition. So maximum power will be transferred to the load when load resistance is equal to the source resistance. Hence, the maximum power transfer theorem is proved. So maximum power is equal to Vs square by 4s is equal to Vs square by 4RL. So the following power, now I am going to discuss about the AC circuit. Generally, in practically, the DC circuits are not there. Generally, AC circuits will be there. In the country, in this, all the communications are at higher frequencies, that is in AC only. So the following, now I am going to discuss about the maximum power transfer theorem in AC circuits. So following power transfer theorem determine the values of load impedances which results in maximum power transfer across the load terminals of an active network. So if a maximum power transfer theorem for AC networks when load with pure variable resistance, okay? There is a no impedance, we are connecting a pure resistance. In that case, what will be the theorem? The maximum power transfer theorem states that the maximum power transfer occurs source to load when the load resistance is equal to the absolute value of active network impedance or source impedance. Consider a network with variable load resistance RL and the source impedance is Rs plus jXs. So the condition for maximum power transfer is equal to RL is equal to under root of Rs square plus Xs square. So here the load resistance, load is only a pure resistor, then the circuit impedance magnitude must be is equal to the load resistance. When the load with variable resistance and reactance, in that case what will happen? When maximum power delivered from source to load impedance ZL is equal to the complex conjugate of the source impedance ZS. See here figure, and here the source impedance is RS plus JXS. Then the load impedance is equal to RS plus JXL. Then the condition is here, RS is equal to RL and XL is equal to minus XS. When at this condition only, the maximum power will be transferred to the load. This is about the maximum power transfer theorem. Now I am going to discuss about some problems on this maximum transfer theorem. See here the problem. Take the problem. Determine the maximum power delivered to the load in the circuit shown. Here there is a small simple problem. In this there is no reactances. All the resistances are there and it's a DC circuit only, and find the power delivered to the RL. See, in the given circuit, let us find Thevenin's equivalent circuit across AB. So from easily we can find out the current through RL. So that is the reason first Thevenin's means we have to open circuit the RL and we have to find out the voltage across the A and B and the resistance in series with the Thevenin's voltage. That is Thevenin's resistance and Thevenin's voltage. So how to find out it? We have to open circuit that RL and 2 plus 3 ohms are in series now. See, the total resistance is equal to 2 plus 3, 5 ohms is parallel with 5 ohms and this combination is in series with 10 ohms. So how much it is? It is, the total will be 12.5 ohms now. So that current, how much current? Current is equal to 50 volts by 12.5 ohms. The total current drawn by the circuit is 50 by 12.5, that is 4 amps. So 4 amps current is drawing from the 50 volts. And now the impedance, the current in 3 ohm resistance is, the total current is IT into 5 divided by 5 plus 5, that is 4 amps into 5 by 10, that is 2 amps of current is flowing through 3 ohm resistance. Once you know the current in 3 ohm resistance, you can find out the Thevenin's voltage. The Thevenin's voltage is equal to, VTH is equal to 3 ohms into 2 amps, that is 6 volts. And now we have to find out the Thevenin's resistance. So Thevenin's resistance is equal to, we have to short circuit the voltage source, then this 10 into 5, this parallel combination is in series with 2 and that combination is in parallel with 3 ohms. So by solving this, how much we will get? So 1.92 ohms. So this can be replaced by a Thevenin's equivalent circuit and the 6 volts in series with 1.92 ohms and is in series with RL. So our problem, what is the problem? Calculate the maximum power delivered to the load. So how much should be the load for maximum power? RL must be is equal to the source impedance, that is 1.92. So the same resistance will be there and the current, next we have to find out the current. See, RL is also 1.92 and 6 volts divided by 1.92 plus 1.92 will gives the current, then that I square into 1.92 will give the maximum power. In this way, we can calculate the maximum power transfer theorem. So, this is very important theorem. We have to always remember, we have to solve that, or in higher advanced subjects also we have to use this theorem. See, next I am going to take another problem 2. Find the value of load resistance when the RL draws the maximum power. Also find the value of maximum power delivered to the load. See, it is a simple problem it is given. So 25 ohms, 50 volts voltage source is in series with 25 ohms and that is connected with a load RL. So for maximum power, how much resistor, how much RL must be and what is the power delivered to the load. So it's a simple problem, so that the source resistance must be is equal to the load resistance for maximum power transfer theorem. And so RL is equal to 25 ohms and we have to find out the maximum power. So the source delivers the maximum power to the load when load resistance is equal to the source resistance. So RL is equal to 25 ohms. Then the current is equal to 50 by 25 plus RL. RL is equal to another 25. So current is equal to 1 amp. 50 by 50. So that is equal to 1 amp. Now we have to find out the maximum power. So 1 amp current is flowing through the RL now. So now the power is equal to, power delivered to the load is equal to I square into RL. What is I? I is equal to 1 amp and RL is equal to 25 ohms. Now calculate the maximum power. I square into RL is equal to 1 square into 25, it is 25 watts. So take another problem. Determine the load resistance to receive maximum power from the source. Also, find the maximum power delivered to the load in the circuit shown below. See here, the load is connected between A and B terminals, that is RL. And here there is a 100 volts source is applied between a bridge network, like 10 ohms, 20 ohms, 30 ohms and 40 ohms is connected like a Wheatstone bridge. See here, determine the load resistance and receive the maximum power from the source. Also find the maximum power delivered to the load in the circuit shown below. So for the given circuit, first we have to find out the Thevenin's equivalent circuit. So in the Thevenin's equivalence, voltage across the A and B. So A, B terminal must be open circuited. So first A and B terminal is open circuited. Then what will happen to the circuit? Ten ohms and 30 ohms are become series and 20 ohms and 40 ohms become series. Then the current flowing through two branches we have to calculate. So 40 ohms and 60 ohms both become parallel. Find out the total current now. So VAB is equal to voltage across 30 ohms minus voltage across 40 ohms. Just then we can find out the VAB. So for finding VAB, the voltage across 30 ohms, the voltage across 40 ohms, is, for finding that we have to find out the currents. So voltage at point A is VA is equal to 100 divided by 30 by 30 plus 10, that is 75 volts. And the voltage at B is equal to 100 divided by into 40 divided by 40 plus 20, that is 66.6. See, again I am repeating this because this 100 or these 10 ohms plus 30 ohms and 20 plus 40, 60 ohms, these two are become now parallel, and the voltage total 100 volts is appeared across 10 plus 30, and the same voltage 100 volts is appeared across 20 plus 40. So the voltage across 30 ohms is equal to, that is VA is equal to 100 ohms, 100 volts into 30 divided by 30 plus 10, that is 75 volts. Similarly, 100 volts into 40 divided by 40 plus 20, that is 66.67 volts. Now the voltage across the AB is equal to the 75 minus 66.67, that is 8.33 volts. That is the Thevenin's voltage here. Now we have to find out the Thevenin's resistance. See, the Thevenin's resistance in this 30 and 10 becomes short because the voltage source is short circuited, and 30, 10 are parallel, and 20 and 40 are become parallel. So from this we can find out that is 20.83. 30 is in parallel with 10 plus 20 is in parallel with 40 is equal to 20.83 ohms. Now the Thevenin's voltage is 8.33 volts is in series with a Thevenin's resistance 20.83. Now this is connected to a load resistance RL. So now I am going to apply now maximum power transfer theorem. So for maximum power transfer theorem, what is the RL? RL must be 20.83, and the power so according to maximum power transfer theorem, RL must be is equal to 20.83. The current drawn by the load resistance is equal to IL is equal to 8.33 by 20.83 plus 20.83. So how much? So it's equal to 0.2 amps. Now hence maximum power delivered to the load is equal to I square into RL. So what is I square? 0.2 amps. What is RL? It is 20.83. So for finding that, I square RL is equal to 0.2 square into 20.83 is equal to 0.833 watts. So in this way, we are solving some problems, and next class we can solve some other problems. So now in this class we discussed about maximum power transfer theorem for AC and DC network in different cases and solved related problems. So maximum power will be transferred to the load when RL is equal to RS, RL is equal to XL, RL is equal to XS. Answer is RL is equal to RS. So take down some frequently asked questions. State the maximum power transfer theorem or prove the maximum power transfer theorem. State the maximum power transfer theorem for AC networks. Thank you.